In this video, we are looking at objects that are in free fall. They are falling only due to the pull of Earth's gravity. And we're going to see that this is going to lead to a set of equations that are very similar to equations we've seen before. Okay, this isn't totally different from the last topic we've been going over, which is objects moving at constant acceleration. This is really just a specific type of constant acceleration. So, first part, a brief history, very brief. These things that I've written down are obviously just paraphrased, they're not quotes or anything. Aristotle, guy who lived about 380 BC. 380 BC. Aristotle had the basic philosophical idea that heavier things fall faster than light things. And to be honest, that's not a bad thought to have. It's fairly intuitive. If you right now took a feather and a bowling ball and dropped them in your room, the bowling ball is almost certainly going to hit the ground first. Okay, so Aristotle, maybe he didn't do a whole lot of experiments, maybe he didn't dive into it, but this idea that heavier things fall faster than light things, okay, kind of makes sense. The first person, though, to really study this, to probably do experiments, to take data, things like that, was Galileo. Now, Galileo lived in 1564. He was born in 1564, okay, AD. That's almost 1,800 years, over 1,900 years actually, between these two people. Now, legend has it that Galileo, who did actually work at the University of Pisa in Italy, legend has it that he went to the Leaning Tower of Pisa and he dropped different sized objects, and he noticed that all the objects hit the ground at the same rate. That probably didn't happen. That's probably just a legend that he actually went to the Leaning Tower of Pisa. But Galileo, doing experiments, did find something very important that countered what Aristotle thought. If you ignore air resistance, or if you're able to use objects that treat or utilize air resistance in the same way, then objects all fall at the same rate. It's not true that heavier things fall faster. Okay, all objects fall at the same rate. And nowadays, when we do these experiments, if we either eliminate things like air, which tend to slow things down, drag things, cushion things, if we can eliminate air, or if we use objects where air resistance would be the same for both of them, think of like two different density materials. Okay, something really dense like gold and something that's less dense like aluminum. They could both be the same physical volume. They could be the same shape, so air resistance would act the same on them. They both fall at the same rate. It is not true that the gold, heavier ball would hit the ground before the lighter aluminum ball. Okay? When we say free fall, by definition, really, we're just talking about objects under the influence of Earth's gravity. We could do like free fall on the planet Mars and stuff like that. Maybe we'll see some problems. But we're just under the influence of gravity. An object sitting on a table is not in free fall, duh, but it's because like the table is supporting it. It's not just under the influence of gravity. The table's helping it out. Okay. Likewise, if something has rockets attached to it, we would not consider that something in free fall. A jet is not in free fall if it's flying because it has rockets as jet engines. Something in free fall is anything that's just falling. The only force tugging it down is the force due to gravity. Okay? This downward acceleration, which is constant, it's so important in our branch of physics that we give it its own special letter, which is this lowercase g. If you're wondering why, in fact, that heavier objects fall the same rate lighter objects, we'll kind of get to that. We'll prove it later on. But one way you could think of it for now is if you have something really heavy, yeah, something that's really heavy has more gravity pulling down on it, but heavy things are also more sluggish. They have more inertia. It's tough to get them moving. And those two things balance each other out. Something that's really heavy, there's more gravitational force pulling it down, but it's also lazier. It has more inertia. It doesn't want to start moving. Something that's light has less gravity pulling it down, but it also has less inertia. It's willing to get going faster. So those two things cancel out, and you can think of it as that's why they fall at the same rate. We'll do a mathematical proof once we get into forces a little later. Okay, I'm continuing with part B. All right, I just said that G is a constant. We give it its own letter. On Earth, it is always 9.8 meters per second squared downward, as long as you're anywhere near the surface of the Earth. Okay, we'll always be plugging in 9.8 meters per second squared down. If we're going to use this in an equation, I mean, yeah, I could write 9.8 meters per second squared down, but I can't really put that into a function. I can't multiply the word down. If we go back to what we talked about before, by convention, upwards is positive. So if this Earth acceleration is always downward, we could say that G is equal to negative 9.8 meters per second squared. Gravity is always, always, always downward. That's why when you drop something off a cliff, it speeds up on its way down. And that's why if you throw something into the air, do it right now, it slows down, right? It slows to a stop at the very peak, and then it starts falling back. Okay? So it's this constant 9.8 meters per second squared. It's a constant acceleration. Well, if you remember the last couple classes, we've been going over problems for things that are experiencing a constant acceleration. This is actually nothing new. We can use the same equations that we learned a couple days ago for constant acceleration for objects that are in free fall, because objects that are in free fall experience a constant acceleration. Nothing is really different. Last slide. Part C. For objects that are in free fall, we saw this part already. We're saying the acceleration is constant, but now we're talking about specifically things that are falling. And we called things that are experiencing Earth's downward acceleration G. Again, G is negative 9.8 meters per second squared. On the left side, these were the equations we already saw. We already know them. I just did one little change. If you think of a graph, the horizontal axis is called the x-axis and the vertical axis is called the y-axis. We use this same notation in physics. For things moving horizontally, we use the symbol x, because x represents things moving on the horizontal axis. So this same equation, v equals v naught plus a times t, just to specify this is for things moving horizontally. We're not ultimately or fundamentally changing anything. It's Vx equals Vx naught plus the acceleration in the x direction times t. Same thing down here. I'm just adding in those little subscripts to be very clear on what direction I'm talking about. The left side is horizontal. Here on the right side, the equations we're going to use for vertical motion. But they're the same equations. The only change I made is that I added in the y. Okay, here is something with a y velocity that equals its original y velocity plus this is where the acceleration went. We know that the acceleration is a constant. So instead of plugging in ay, I can just plug in g. Right? So these are our new equations, quote unquote, but they're really the same thing. Okay? If we say that up is positive, which is our convention, then we'll always plug in 9.8 into these equations, negative 9.8, excuse me. And we'll always ignore air resistance for these problems unless you're told otherwise. You'll never have to ask, like, oh, Mr. Thrasher, are we assuming that things are falling at negative 9.8? Unless the problem or I say something contrary, you can always assume for something that's falling, the acceleration is negative 9.8. We'll be getting practice using these equations, which again aren't very different from the last ones, in the next couple days. Thank you.